Hey everyone, in this video we're going to be talking about surface integrals. So let's jump right into it. So let's define a surface integral. So surface integral over a curved surface in space, it essentially is the two-dimensional extension of the line integral. So this is what we've learned previously, of the line integral over a one-dimensional curve. Okay, and so some of the things that we use these surface integrals for, they can be used to compute the mass of a surface, or maybe the flow across a curved membrane, or we can use them to determine the electrical charge on a surface, and many other uses. So let's begin with discussing that there's actually two forms for our surface integrals. So I'll say form number one is a surface integral of scalar functions, and the second one is going to be surface integrals of vector fields. So surface integrals of vector fields. So let's go ahead and look at the computation for this. So we're going to define our surface integral of the function, we're going to call it g. So of the function capital G, and this is going to be over the surface that we'll call S. Okay, so what that's going to look like is our double integral over our surface S, and in our integrand here we're going to have our function g of x, y, and z, and then d sigma. And we learned about that last time. That was our surface area differential. And so if we break down this double integral here, this is actually the limit of this Riemann sum. So this is just going to be like the area of a patch on our surface times the function evaluated at a point on the surface. And so that's more of our formal definition for our surface integral. And so the meaning of this pretty much depends on the application. So let's say g is some constant, then this is going to give us the area. If g represents like mass density, then this integral will give us total mass. If g represented charge density, then this integral will give us total charge. So I'm going to give you different formulas for evaluating our surface integrals, and it depends on how your surface is described. So I'm going to say formulas for surface integrals of scalar functions. Alright, option number one. Let's say that S, our surface, is defined parametrically. Okay, so again, you're going to use different versions of your surface integral based on how your surface is described. And so what that looks like, and this is from the last video, we have a vector equation or function that finds the points on our surface, and so that's going to be f of uv for the I component plus g of uv for the j component plus h of uv for the k component. And so our surface integral, double integral over our surface of g of x, y, z, d sigma, in this case is going to be evaluated as a double integral over region R of our function g, evaluated at the components from our parameterization. So g of f of uv, little g of uv, h of uv, to plug those into our function. And then our surface area differential was from before in the past, the partial derivative of r, the parameterization with respect to u, cross with partial derivative with respect to v. Cross that and find the magnitude, and then du dv. Okay, and then this is just where r of uv is belonging to the real numbers. Okay, so this would be, I'll say, one version for evaluating your surface integral if you have your surface defined parametrically. So you would want to use this version right here. So let me go ahead and give you version 2. Version 2 is going to be if S, your surface, is given implicitly. And that's going to look like f of, let's say, xyz equal to 0. So our surface integral of g of x, y, z d sigma can be evaluated using a double integral over region R. And then we have the magnitude of the gradient vector of our surface divided by the magnitude of the gradient vector dotted with p, and that's going to be dA. Okay, so let me mention this again. We saw this in the last video, but where p is a unit vector perpendicular or normal to your region R. So for example, if R is in the xy plane, p would be pointing upward or downward, so you could use the unit vector k. So here's what I just said in case you want to see it. Let's say R is down here in the xy plane. Okay, then p would be perpendicular to this, so pointing upward, so we could use the unit vector k in that case. Okay, so this would be how you evaluate your surface integral if your surface is defined implicitly. So let's do one more version here, and this is going to be if S, your surface, is given explicitly. And so that one might look like z equal to f of xy. And so in that case, your surface integral, double integral over your surface, g of x, y, z, d sigma, can be evaluated as your double integral over R of your function g, and you have x, y, and then you plug in what z equals in terms of x and y. So we'll just say that that's f of xy. And then you have in the back here square root of partial derivative with respect to x from your function f squared plus partial derivative with respect to y squared plus 1 and then dx dy. So that pretty much takes the place of your surface area differential here, and we did talk about that in the last video as well. Okay, so this would be how we evaluate our surface integrals if our surface is defined explicitly. So 3 different options. Alright, let's do an example. So we're going to integrate the function x squared over the cone z equals square root x squared plus y squared, where z goes from 0 to 1. So what we're going to do is we're actually going to parameterize this curve using a vector function of 2 variables, and then use version 1 of our surface integrals. And the reason for this is because it's going to be easier to do it this way than if we leave this in explicit form, and I'll show you that way at the end here. So let's just go right into parameterizing this cone, and we learned about parameterizing a cone in the last video. So this could be our parameterization right here, and then this is our k. When we have, for this cone, we want r between 0 and 1, and then theta is going to be a full circle, so between 0 and 2 pi. And then the magnitude of the cross product of our partial derivatives, r sub little r, so this is this function r, partial derivative with respect to little r, cross with the partial derivative with respect to theta, is just going to be square root 2 times r. And we worked examples out about that last time, so if you want to just review that on finding the partial derivatives, taking their cross product, and then their magnitude. Okay, so we're going to jump right into our formula, and just note that S is defined parametrically. So this means we're going to use, I'll call it version 1 of our formulas for evaluating our surface integral. And so our surface integral of x squared d sigma ends up being this double integral over our region R, where we have g of r theta, and then multiplied by this magnitude of the cross product, dr d theta. So just a quick reminder, this is our surface area differential right here. All right, so plugging in what we have for this function over the cone, we end up getting, on the outer integral, theta goes from 0 to 2 pi. On the inner integral, r goes from 0 to 1. And then our function is just x squared, but because we're working in terms of r and theta, we're going to say that that's r cosine theta squared. We want to rewrite our function here in terms of r and theta, and we know from polar coordinates that x is r cosine theta. And then we can have our magnitude of our cross product, that's just square root 2 times r, and then dr d theta. Okay, so this is the double integral that we're going to have to evaluate. So let's simplify a little bit and then just work through this evaluation. Okay, so this is going to be r cubed. Let's bring out that square root 2 to the front here. Cosine squared theta, dr d theta. Okay, integrate real quick with respect to r, and square root 2 is still in the front, 0 to 2 pi there. That's going to be r to the 4th over 4. We still have a cosine squared 2 theta there. Evaluate from r is 0 to 1, and then don't forget our d theta. So that's going to give us, and I'm going to factor out the 4 on the bottom here, square root 2 over 4, and then we have just cosine squared theta, d theta. All right, now remember how to integrate this. We want to go ahead and use some of our trig identities, and we're going to let cosine squared theta be replaced with 1 plus cosine 2 theta over 2. So that would give us the following, square root 2 over 4, 0 to 2 pi. That's going to end up being 1/2 plus 1/2 cosine 2 theta d theta. All right, and then we can separate this into 2 integrals, and then we're almost done here. So square root 2 over 4 times the integral of 1/2 d theta plus square root 2 over 4 times, let's just bring out that 1/2, integral from 0 to 2 pi. And let's go ahead and let cosine 2 theta, let's let 2 theta be u. And so then we're going to need to divide by a 2 when we do that substitution. So I'm just letting u equal 2 theta. So du would be 2d theta. Okay, and so we get square root 2 over 4. Let's just factor that all the way out to the front. 1/2 theta, evaluated from 0 to 2 pi, plus 1/2 times 1/2 sine 2 theta, evaluated from 0 to 2 pi. And after we simplify and plug in our limits of integration, we are going to get pi times square root 2 over 4. Okay, so that is the value of our surface integral. So like I mentioned earlier, we could have used the explicit version that was already given to us and integrate that way, but let me just show you really quick why we ended up rewriting this in parametric form, because it was a lot easier to integrate. Let's go ahead and try another example. So we're going to integrate the function 6xy over the plane z equals 6 minus x minus y in the first octant. So I drew a little bit of this for us, and so we have that there's actually values here. This goes to 6 on the x-axis, this goes up to 6 on the y, and also goes to 6 on the z-axis. And we know that because we're in the first octant, x is positive, so is y, and so is z. And so our surface is just this part here. And so our surface is defined explicitly, and we will use version 3 of our surface integral formulas. So that's right here, and notice what I just plugged in for z was our surface. So let's go ahead and figure out our partial derivatives first. So our surface z is what we're calling f, so partial derivative with respect to x is just going to be -1. Partial derivative with respect to y is also -1. And so if we plug those in here, we're going to get 1 plus 1 plus 1 square root of 3. Okay, so that's going to be in our integral. And then our function, g of x, y, 6 minus x minus y is just going to be 6x, y, because there was nowhere to plug in for z, so we didn't have to do anything with that value there. Now our double integral, we're going to have our limits in terms of x and y. So y, we'll go ahead and put that on the outside. But for x, let's go back to our image over here and just draw what would be happening in the xy plane. So if we look at the shadow of our surface here, in the xy plane, it looks like this, where we have 6 here, 6 there. So we would be entering our region when x is 0 and exiting at this line, y equals minus x plus 6. And let's just go ahead and solve it for x. So we have x equals 6 minus y. So our limits for x go from 0 to 6 minus y. And our integrand is just 6xy square root 3 and dx dy. Okay, so that's our setup. Let's go ahead and just integrate real quick. So we have our inside integral is going to become 3x squared y square root 3, evaluated from 0 to 6 minus y. And then if we simplify that and plug in our limits, we're going to get 3 square root 3 times 36y minus 12y squared plus y cubed. Then we'll integrate one more time with respect to y this time. And then we get 3 square root 3 times 18y squared minus 4y cubed plus y to the 4th over 4. Evaluate that from 0 to 6. And once you do that and plug in and simplify, you're going to get final answer 324 square root 3. That's the value of our surface integral. Okay, so now we're going to be talking about the orientation of a surface. So first consider a curve. We're calling it C, but it's parameterized as R of t. And a natural orientation for a curve is the direction of increasing t. So as t increases, that is our natural orientation. And then our unit tangent vector, t, always points in the forward direction. All right, so this is for a curve. Now let's extend these ideas to a surface. And so consider a surface S, parameterized as R of uv. And so what you want to do is you want to specify a normal vector. And this will be at each point on the surface S. And that's going to be relatable to our tangent vector for our curve. And so what is the normal vector? Well, we can use the partial derivative of r with respect to u cross the partial derivative of r with respect to v. And that's going to be a vector that's normal to our surface, and it will give an orientation. And so what we're talking about here is an orientation for our surface. And so an orientation is just a way of choosing one of two sides of a surface. Okay, so let's go ahead and give this definition. And we're talking about this because it's going to help us with our surface integrals over vector fields. So a smooth surface is called orientable or two-sided if we can choose a continuous field of unit normal vectors on the surface. All right, and so if we have a surface with a consistent choice of sides, it's just called an oriented surface. And so an example of a non-orientable surface would be a Mobius strip. It's actually considered one-sided. So now we're ready to talk about our surface integrals of vector fields. So our surface integrals of a vector field, let's just give some fine print here that we use for our definition. So f is going to be a vector field. It's going to have continuous components, and this is going to be defined over a smooth surface S, having a chosen field of unit normal vectors that orient S. Okay, so that's why we needed to talk about oriented surfaces, because it plays a part in our definition for surface integrals of vector fields. pretty much what this is saying is that F is a continuous vector field on some region in space containing the smooth oriented surface. And so here is what we have for the surface integral. So the surface integral of F over S is equal to the double integral over the surface of F dotted with N d sigma. So remember, d sigma is our surface area differential. And so we actually have other versions of this, and so what this could be representing is actually flux. So this integral equals the flux of the vector field across the surface S. So this is the flux of the field F across S, and we can evaluate this surface integral as a double integral over the region R, where F is dotted with partial derivative of R with cross with partial derivative of R with respect to U and V. So that cross product there, du dv. So this would be for a parameterized surface. And we're pretty much just replacing N and d sigma. So I'll just say this is because N is your unit normal vector, which would be partial derivative of U, R with respect to U, cross partial derivative of R with respect to V, but it's a unit vector, so divide by its magnitude. And then if you substitute that into the equation up here, and then substitute what d sigma is, that's how you get this other version for your surface integral. Alright, so this is going to be our definition and calculations that we'll use. And just a quick note, if S is part of a level surface, so that G, we'll say G of x, y, z equals some number C, then what we can choose for N, for our unit normal vectors, we could say that N is either the positive or negative of the gradient vector divided by its magnitude. And just choose N based on whatever your preferred choice is and which way it points, either positive or negative. Let's go ahead and do this example. So we're going to find the flux of the field F equal to yz for the I component plus x for the j component minus z squared for the k component through the parabolic cylinder y equals x squared, where x is between 0 and 1 and z is between 0 and 4, and then n is going to point outwards. So just so you get a visual for this, you have part of a cylinder here in 3D space, and it basically is just like something like this. So you just have your curve here. This is y equals x squared, and we go from 0 to 4 for z, and so it's just this surface here. Let's label some points. These are 1 and 1, but this is up here at 4. And so n is pointing outward from the surface, so this direction. Alright, but if we can parameterize, we can use the second version of our formula that we talked about for flux, so we can use this version. So the double integral of our field dotted with the cross product, r sub u cross r sub v du dv. So let's go ahead and start there. We're going to parameterize our surface. So we know on the surface that x is just x, but we know that y is x squared, and then z can just be z. So we have a really nice parameterization if we just say that r is of xz. And so for the I component, we can just say that's x. But for the j component, we can replace y with x squared, because that's what that equals. And then for the k component, z is just z. So that's going to be our parameterization, and then we know that x goes from 0 to 1, and z goes from 0 to 4. Okay. So now let's just break down our steps that we're going to need to evaluate this integral. So next, we're going to go ahead and need the cross product. So I'll say now compute r sub u cross r sub v. For us, that's r sub x and r sub z. So first find the partial derivative of r with respect to x. That's going to be 1 for the I component, 2x for the j component and 0 for the k component. And then our partial derivative of r with respect to z is going to be 0 for the I component, 0 for the j component, and 1 for the k component. Alright, and then we just need to cross these. So r sub x cross r sub z. Just fill out our 3 by 3 determinant real quick with the vectors we just got. So this is going to be 1, 2x, and 0 in row 2, 0, 0, 1 in row 3. And if you work out this cross product, you're going to get 2x for the I component minus 1 for the j component. Alright, so then what do we need? We need to write f in terms of u and v. So that's not going to be too much work for this one. We're just going to say that f is, instead of y times z for the I component, if you just go back up here to what f was, I'm just looking right back at this one here. So instead of the y, we're going to go ahead and replace that. So we know that that's x squared times z for the I component. And then we have just x for the j and minus z squared for k. Okay, so what do we need next? We should go ahead and just compute the dot product, because we are going to need to integrate that. So let's compute the dot product of f dotted with r sub u cross r sub v. And so for us, that's going to look like, let's go ahead and go to angled bracket form just to make it easier to look at. F is x squared z for the I component, x for the j component, and negative z squared for the k component. Dot that with our cross product vector. That was 2x for the I component, negative 1 for the j component, and 0 for the k component. So I'm just looking here for this one and here for this one. Alright, and if you do this dot product, you will get 2x cubed z minus x. So finally, we're ready to integrate. So now we're ready to integrate because we did all of the work to get to our integral. And so we have our double integral, and x goes from 0 to 1, z goes from 0 to 4, and our integrand is 2x cubed z minus x, and we'll do dx dz. Alright, so getting here was the hard part, but now that we're here, we can integrate this pretty quick. So we have x to the 4th times z over 2 minus x squared over 2. Evaluate that from 0 to 1. And then you're going to get the integral from 0 to 4 of 1/2 z minus 1/2 dz. Integrate that, and we'll get z squared over 4 minus 1/2 z. Evaluated from 0 to 4. Final answer 2. Okay, let's take a look at one more example. We're going to find the flux of this field outward through the surface S, which is going to be cut from the cylinder y squared plus z squared equals 1, where z is positive, and it's cut by the planes x equals 0 and x equals 1. So what that looks like is this cylinder over here, and we've cut it at x equals 1 and x equals 0. And then our normal vector to this surface is going to be outward like this. So this is n. So what we want to do first is find n. And so what we can do is we can find an outward normal field on S using n equal to the positive of the gradient over its magnitude. Okay, so if g is y squared plus z squared, then the gradient of g is just going to be 2yj plus 2zk. And then the magnitude of this is going to be square root of 4y squared plus 4z squared. And so n is going to look like 2yj plus 2zk over 2 square root 1, which is just yj plus zk. Now for this integral, what we're going to need, so to compute the double integral over our surface of f dot n d sigma, we just found n, we were given f, but d sigma, we had this from the previous video, so reminder that our surface area differential for this form is going to be the magnitude of the gradient of g divided by the dot product of the gradient of g with p, that magnitude, dA. And so real quick from last time, what p is a vector that's perpendicular or normal to r, where r is the region, like our shadow, that we integrate over. So going back up to our image here, this part would be r. So r is in the xy plane, and so for us, p, a vector that's normal to that, could just be the vector, unit vector k. So for us, we can just fill this in. We now know that this is 2 on top, and then we're going to have the magnitude of the gradient vector g, which was 0, 2y, 2z. Dot that with p, and p is perpendicular to the region r, and so that's just going to be the vector, unit vector k, so 0, 0, 1. And when you do that dot product, you end up getting 2 over magnitude 2z, which is always going to be positive since z is greater than 0. That was given to us. So this is just going to be 1 over z. Don't forget our dA. Alright, so putting this all together, we have the double integral over our surface, where we have f dot n d sigma. So f was 0 y z z squared, dot that with n, which was 0 y and z, and then d sigma was 1 over z, and this is, we'll leave that as dA for just a minute. And real quick, just to show you what we were doing here, this was from the given one right back up here, and then over here was n. Okay, and then we just did this, all this work to find d sigma, which was that part. So let's keep going, we're almost there. So double integral, we have y squared plus z squared dA, and this was given originally as well. This was just 1, so all of this becomes the integrals of 1, and we'll do dy dx. If you go back up to our drawing here, y goes from -1 to 1, and x goes from 0 to 1. So -1 to 1, 0 to 1, and we're going to get final answer of 2. And just so you know, it is a coincidence that it's the same value from the last example. Alright, so the last thing to mention is just some formulas, and we've seen these actually before, and there's just a little new part here. So this is for mass and moments for very thin shells. And so we have a formula for mass, for the first moments about the coordinate planes, about the YZ plane, XZ plane, and XY plane. We also have coordinates for the center of mass, so the center of mass in 3D would be the X bar for the X coordinate, Y bar, and Z bar. And then we have second moments, or moments of inertia, so second moment about the X-axis, Y-axis, Z-axis, and then about a line L. And then for this one, just note that R represents the distance from a point to the line. We have seen these in the past, and the new part is just that now, from before, we used to have our volume differential, and so now the new part is just that we're replacing that pretty much with our surface area differential d sigma. Okay, so that's it for this one. Thanks for watching.